So in this module, we're going to talk about model building process and principles. So for the model building process, we're going to really give a step-by-step way to approach building a model. And we're going to really dive into the details and show this. So first we're going to talk about it, and then we're going to actually do it on a notebook with real data. But along with this, I'm going to try to convey some of the principles behind this model building process. In other words, why are we doing it this way? And what are the goals? What do we hope to achieve by approaching model building in this fashion? So let's talk about the goals of this model building process. So the first goal, and what I think is a really, really important goal, is to build confidence in your understanding of the data. And this is something I feel very strongly about. If you're working for a business and that data is really key to understanding some aspect of that business, you really want to understand the data. And as you work with it more and more, you should really build your understanding of it and build confidence that you know what's going on inside the data. So if you just start with a process where you sort of blindly amass all the data and throw it into some modeling process and not look at it, not interact with it at all, you're never really going to build much confidence that you understand what's going on. So the process that we're going to talk about is really going to help you interact with the data, help you understand what's going on. Now, a related goal of this model building process is to expose problems or issues with the data. So again, if you just throw everything into a big model building thing and you don't explore the data, you won't know what problems or issues are there, and you won't be able to understand them or deal with them. And so that's another thing this process that we're going to go through will enable, is that you'll interact with the data over and over again, and you'll gradually start understanding where there may be problems, shortcomings, issues, or just idiosyncrasies, and then you can use that information to improve your model building. Another goal of this process is that it will enable model improvements via feature engineering or just via adding new features and so forth, because you'll be able to see where the model is doing poorly, where the model is doing well, and you'll be able to target your model improvements towards those cases where the model is doing poorly. And another advantage of this process is that you will sort of naturally be able to balance your model complexity against your performance. So often model complexity is not something people think about. People say, my goal is to get the best performing model. I've got this metric. I want to get the highest possible score of the metric. So let me just throw all the variables in there and try my best to get the highest possible performance, the highest possible number on this metric. And this approach is often misguided, because if you have a model which uses 7 variables and does almost as well as a model which uses 200 features, you're much, much better off using the simpler model in production. Because the reality is, going forward, if you've got 200 features, that's 200 possible ways that errors could enter your model. That's 200 ways that your model could fail because one of those data feeds goes down. And it also means it's actually something that's more likely to have performance decay over time, to deal with model drift and stuff. The more complicated the model, again, the more things that can go wrong with it, the more chances for problems to enter it. So having a simpler model, if you're getting most of the performance out of it, is really important. And this model building process that we're going to go through kind of naturally builds up models that increase in complexity, and you can see the trade-off of complexity versus performance. Okay, so let's talk about this model building process, and we're going to go through step by step. So I'm going to describe the steps here, and then we're going to go into a notebook and really see these steps in action. So the first step is always to explore and interrogate your data. Now, by interrogate, what I mean is that you look at the data, you look at the relationships of the different variables, and then you ask some questions. You try to use your curiosity and say, I see this pattern, does this mean this particular hypothesis? I have a hypothesis that might explain why this is happening. And then you ask some questions of the data. you say, well, if this hypothesis is true, then I should see this thing. Let me do some calculations. Let me run a couple commands. Let me do a few plots and see whether that's true or not. And this process will help you build confidence that you understand the data, and will just in general build comfort and expertise about this data set. So it's really important to have a process that allows you to explore and interrogate your data. And this is an ongoing thing. I think it's the first step, but it's also something you should do periodically as you work with the data set. Spend some time asking new questions that have arisen from what you've learned in the past. The next step is to build a simple baseline model. Now, this is the mistake that a lot of people make, is again, they want to build a model and they've got all these features. So the first thing they do is say, I'm going to take all the features and put them into some massive process and let some big model building process run, and then at the end I'll get a model, and you look at the performance and you say, yeah, it looks good. But you don't really know if it's good or bad because you don't have anything to compare it to. So what you really want to do is make sure that you have some baseline to compare it to. So this baseline model is going to be something using relatively few variables and usually a relatively simpler method, just to get a sense of what could I do really simply and really easily, and then how much better can I get by doing some of these more complicated techniques. Now we're going to start building a gradient boosting model, and again, this step is focused on gradient boosting. And we've talked about how gradient boosting, that there's a lot of hyperparameters, but we talked about how there's three that are really the most important, that it's the number of trees, the number of estimators, the learning rate, and the max depth. And we're going to show how to use early stopping that lets you really handle the number of estimators and the learning rate very simply. And then you only have to fit the max depth. And we're going to focus on just getting kind of these three parameters right. And then later at the end of the process, we'll build in all the other hyperparameters to try to see how much further we can push it. But at the early stage where you're kind of figuring out the features, trying to do some feature engineering, trying to understand the data and the model, you don't want to be doing this full hyperparameter search every time. So after you've built this model and fit the max depth, then we're going to do some evaluation of it. And we're going to compare the results to the baseline model that we have and other previous models that we built. And this, again, will build up our trade-off between model complexity and performance. We'll be able to see that when we added in certain features, we either got a big jump in performance or we got a relatively small jump in performance. And we'll be able to know how to trade off this model complexity and the performance. And this will also build confidence. We'll build a story where we can say, with this small set of features, we got this performance, we add in these features, we got this performance, and so forth. As you build that story, and as long as it holds together, then you feel confident that you understand what's going on. And you'll be better able to recognize when something goes wrong, if you've made a mistake or not. Another thing we'll do with evaluating the model is what's called failure analysis. So this is where you look at cases where the model did poorly. And this is really important for improving the model. One way to improve things is you look at the mistakes and try to fix them. So we're going to look at cases where the model did poorly and try to analyze whether we see any patterns in these cases. And that might shed light on how to either add new features or even engineer new features that would then improve this performance. And this is where we're going to use our human brains and use our domain expertise to guide the model building process. And through this, we will iterate and improve the model. So we'll come up with different models with different sets of features, and we'll evaluate them and have different levels of performance. And at a certain point, we'll be able to say, here's where I want to be. Here's the best trade-off between complexity and performance. And once you've done that and you decided this is the model I want to go ahead with, then you can do the final hyperparameter tuning and really spend a lot of time churning around and trying to squeeze those last few drops of performance from your model by doing that final hyperparameter tuning. Okay, so next we're going to go into a notebook and we're going to really dive into showing these steps on a real data set. Okay, so we're going to go through a notebook now, where we're going to actually open up a data set and play with it and kind of go through this process as if we were building a model using this process. So to get started, if you could clone the repo at the address I have here, www.github.com/numeristical/resources, and then you'll navigate to the folder Building GB Models and open the notebook file, which is the notebook I have up here called buildgbmodel.ipynb. You'll be able to follow along directly. So we're going to do a bunch of imports to start, and we're going to be using the Ames housing data. So this is a smallish data set, about 3,000 data points about houses sold in Ames, Iowa from 2006 to 2010. So we're going to take that data, and you can see it has quite a lot of variables, quite a lot of predictors. And then at the very end, we've got the sales price. So that is the price of the house, and that will be what we're trying to predict. So we can take a look at just a few data points. So we'll pick 5 random data points, and again, you can see these different variables. We've got things like the neighborhood, the type of building, overall quality, overall condition. We've got a lot of these variables here, so we're not going to look at all of these right now. Instead, so here's the list of all the different variables, features that we have in this data set. So to start, we're going to just focus on a smaller subset of features. So we've got the lot area, it's the size of the lot the house is on, the overall quality, that's a numerical number, a score that I think a real estate agent assigns to the quality of the house, overall conditions similar, what condition the house is in, the year the house is built, the year it was remodeled or added onto, graded living area. So this is essentially the legitimate square foot of the house, that's the square footage of the house that counts as living area. The number of full baths, number of half baths, the number of bedrooms, the size of the garage, and the number of fireplaces. So this is again just to start with something simple and tractable. And we're going to break into train and test sets to start, just to get that all ready. And so you can see if I now focus on just my X, I have just these 10 predictors now. So let's review quickly our model building process, and then we're going to go through to these steps. So again, we want to start by exploring and interrogating the data, building a baseline model. Then, starting our gradient boosting process, we're going to build a model and use early stopping and tune the max depth. We're going to check where the model is doing poorly. We're going to try to engineer some features to address those model shortcomings. We're going to use our domain expertise and our common knowledge and just our thinking. And then we're going to save the big hyperparameter tuning until the end. So once we've done a few iterations and we like where the model's at, then we'll do that big hyperparameter tuning. So first, let's talk about exploring and interrogating the data. So let's give a little more detail about what we mean by that. So just the common things to look at your data before you do the modeling. It's amazing how many people do not ever do that. They don't look at the data. They just start pouring it into the model and seeing what scores they get. One thing, so here's some simple things you should always do. You should understand the distribution of the target variable and know its mean at a minimum, right? You should look at the relationships between the target and your individual features. You can look for idiosyncrasies or other artifacts in your data. You can try to understand what different values mean, and we'll see that. Sometimes there's a number that you might have a 0, and that 0 might actually mean 0, or maybe the 0 means it was missing. So you want to understand that before you dive into your modeling, because what the 0 represents might have implications for how you want to treat it in your modeling process. So this is a regression problem. We're trying to predict the sale price of the house given these features about the house, how big it is, how new it is, so forth, how big the lot is. So we're going to go through some of these steps now. So first, let's get the mean of the target variable and the min and the max. So we see in this data set $180,411. So about $180,000 is the mean price of the house. The smallest, the cheapest house in this data set is $12,000, and the most expensive one is $625,000. So this is important because you want to know when I see a house that's $300,000, it's important to know that, oh, this is a bigger than average house, or a better, more expensive than average house. So just knowing the mean isn't enough, though. We should really understand the distribution of our target variable. So we can make a histogram. Now, one thing when you use plt.hist, just with its default settings, it'll usually give you a histogram like this. Now, I don't really like this histogram for a few reasons. One is that the bins are at kind of weird endpoints. Like I don't know, this bump doesn't line up with like a round number or anything, so I don't like that too much. And this tends to be a little coarse in terms of the number of bins. We've only got about 10 bins here. So what I typically do is I'll plot it once, and then I'll try to come up with a smarter set of bins. So in this case, I see that, okay, my histogram kind of stretches. Well, I know it goes up to 625,000. So just to be conservative, I'm going to set my bins to be from 0 to 700,000. I'm going to have 70 bins. So I have to add 1 because if you want 70 bins, you need 71 bin points. But what this will do is essentially give me bins of size 10,000. And we can do this histogram. And you see this is a lot nicer. And you know, I could see, for example, when I look at a little bump over here, I could see, oh, this bump is exactly from 500,000 to 510,000. If I see a little spike here, I could kind of come down and figure out exactly where that is. So you can see that this is skewed a little bit, right? The mean was 180,000, but if you look at this peak, that's a little bit less than 180,000, which kind of makes sense because the house is never going to be worth less than 0, but you could have some that have a very high price. So you have this long right tail in the way that you don't have a long left tail. So that means your mean is typically going to be a little higher than your median. Okay, so next function I like is in Seaborn, this pair plot. Again, it's a good thing to use when you've got, you know, about this size, about 10 or so variables, predictors. And we're going to run this, and it's going to take a few seconds to run. Okay, so it finished. It took, you know, about a minute and a half here. And what we see here are the variables are features that we're going to use as predictors, plus the sale price all the way at the bottom here. And we've got basically scatter plots of every pair of variables. And this is really useful. So what I like to do first when I do something like this is to look at my target and look at the relationships between each of the features and the target. So we can see for the lot area, one issue with this plot as it is now is that we've got a few outlier values that are causing most of the data points to get kind of smushed into one small section of the graph. So we'll replot that later to sort of get a better look at that. But let's move on to the other variables. Overall quality. Here you can see from this plot that, well, overall quality, you can see that it's integer valued between 1 and 10. And you can see a pretty significant relationship, right? As these numbers go up from 1 to 10, the range of sales prices is going up accordingly. And, you know, with a pretty strong slope. So this suggests that this is going to be a pretty informative variable. Now, if we look at overall condition, you see that this is also integer valued. But you see we have this kind of idiosyncrasy here. There's a lot of values at 5. So this bar of 5 has a big range, and it suggests a few possibilities, right? It might be that somehow a default value of 5 got put in a lot of times if they didn't know the answer. Or it could be that when people fill it out, some of the people who were creating this variable just put 5 for every house because they didn't really want to be bothered with it. I don't know what the suggestion is, but it's important to know for your modeling that 5 is kind of a much more common value, and that, you know, even a lot of very expensive houses still have an overall condition of only 5 out of 10. Moving on, you can look at this year built. And you can see there's a positive relationship, but you see this big kind of jump at the end. So there's a lot of new houses, and most of these very expensive houses, the expensive tail of houses, all seem to be these relatively new houses. So you don't have that many expensive old houses. Year remodel added, we see kind of a similar pattern. Greater living area, so this is the greater living area, that's the square footage. So we see a pretty, solid, significant relationship. Again, that makes sense, right? Whenever real estate agents talk about housing prices, they usually talk about price per square foot. So of course you're gonna, the square footage is gonna be really, really important to the value of the house. We see number of full baths goes from 0 to 4. Number of half baths is just 0, 1, and 2. Number of bedrooms, you can see ranges from 0 to, looks like there's even 1 and 8. And again, you see sort of some correlations, but looking at these, you don't expect these to be super duper strong. The garage area, so here we see an interesting thing. It seems have a pretty strong relationship, but again, a lot of zeros, so these are probably houses that don't have garages. So that's sort of an interesting thing to note. Fireplaces, again, a little bit of correlation, nothing too big. Now, after I go through the relationship with the sales price, also just kind of scan these plots and look for any interesting things that pop out. So one thing that pops out here is this year remodeled added plot with year built. So we see this, very strong, like straight line with a bend to it, right? And you spend some time thinking about it, you realize there's two things going on. This angled part is an artifact of the fact that a house can't be remodeled before it's built, which makes sense. So, and presumably, if the house has never been remodeled, they're going to put in the year built as the year it was added to or remodeled. So that's why you get this line, this diagonal line. So the houses on the line are probably houses that have never been remodeled, and the houses inside are houses that have a different date for remodeled added than they do for year built. Another thing we see is that there's this line bends here, and we have this sort of flat line at 1950. So this suggests that they never put in anything below 1950 for this variable. So this is for the year remodeled added. It's never below 1950. So that suggests that if the house was built in 1900, they still always put the year remodeled added as 1950. So presumably, if they didn't have, maybe they didn't have any records of the building records before 1950. So if they had a house from 1910, when they were creating this variable, they just said, we'll say it was remodeled in 1950, because we really don't know. So again, this is another important thing to know about your data and how it was modeled, because the year 1950 here has a special meaning. It means kind of they don't know, but the house was built in 1950 or earlier. So I hope this shows you what I'm talking about and why you can explore data and interrogate the data. And so if we wanted to, we could dive deeper into these and ask more questions about it. Let's go back to the lot area. So again, for the lot area, this plot is not really that great to look at. So let's redo the plot and change our X limits so that we can see a little better. So now we can see, okay, this seems to be a fairly important variable. As lot area gets bigger, the house tends to be more valuable.